Computer Science 410, Instruction Sets, Addressing Modes and Formats. This is Chapter 13, Part 2. In the last presentation we covered sections 13.1 and 13.2. In this section we'll cover 13.3, 13.4, and 13.5. So back in section 13.1 we looked at different addressing modes. These were immediate, where the operand was equal to the address. It required no memory reference, but we had limited operand magnitude. There was direct, which you can see in B. Here the effective address is equal to the address. And this is pretty simple to implement, but you actually have a very limited address space. Indirect, the effective address is equal to the address specified at the address from the instruction, so the contents of the address. This gives you a large address space, but you need to make multiple memory references, and here you can see in figure C that there are two of those. Register addressing mode, the effective address is equal to the register, and the register will hold the operand. That has pretty limited address space and makes pretty heavy use of the register, so you can't use them for other tasks. Register indirect, the effective address is equal to the contents of the register. So you get a large address space, but it does have that extra memory reference. Displacement, the effective address is equal to the address plus the contents of the register. It gives you flexibility, but there's a lot of complexity in actually implementing that one. And last but not least, the stack, where the effective address is the top of the stack. You don't have any memory references, but it has limited applicability. So let's take a look at some of the instruction formats. So an instruction format defines the layout of the bits of an instruction in terms of its constituents fields. An instruction format needs to include an opcode implicitly and or explicitly 0 or more operands. So you need to have 0 or more operands there. Sometimes you don't have an operand, sometimes you have multiple. Each explicit operand is referenced using one of the addressing modes that we talked about in the previous slides. The format needs to indicate the addressing mode of each operand, and for most instruction sets more than one format is actually used. The design of an instruction format is a pretty complicated thing, and there are an amazing variety of designs that are out there that have been implemented. We'll take a look at those, including some of the different architectures and how they've implemented them, and examine the X86 and ARM solutions in a bit of detail, as we always do. Let's look at some of the design issues, beginning with instruction length, which is probably the most important. And this is the most basic design decision. It affects and is affected by memory size, memory organization, the structure of the bus, processor complexity, processor speed, and it should be equal to the memory transfer length, or one of them should be a multiple of the other. It should also be a multiple of the character length, which is usually 8 bits, and of the length of fixed point numbers. So the most obvious trade-off here is between the desire for a powerful instruction repertoire and need to save space. Programmers want more opcodes. They want more operands, more addressing modes, and greater address range. More opcodes and more operands make life easier for the programmer because shorter programs can be written. Similarly, more addressing modes gives the programmer greater flexibility in addressing certain functions, such as table manipulations and multi-way branching. And of course, with the increase in main memory size and the increasing use of virtual memory, programmers want to be able to address larger memory ranges. All of these things require bits and push in the direction of longer instruction lengths. But longer instruction lengths can be wasteful. A 64-bit instruction occupies twice the space of a 32-bit instruction, but it's probably less than twice as useful. Beyond this basic trade-off, there are some other considerations. The instruction length, again, should be equal to the memory transfer length from the system bus, or one of them should be a multiple of the other. And another important feature is that it should be a multiple of the character length, which is usually 8 bits, or of the length of the fixed point numbers. So again, the trade-offs here are complex, and there are different points to having longer instructions and different points to having shorter instructions. So for a given instruction length, there's a trade-off between the number of opcodes and the power of the addressing capability. The following factors go into determining the use of the address bits. How many addressing modes do you have? Sometimes an addressing mode can be indicated implicitly. For example, certain opcodes might always call for indexing. In other cases, the addressing modes must be explicit, and one or more of the modes will be needed. Number of operands. We've seen that fewer addresses can make for longer, more awkward programs. Typical instruction formats on today's machines include 2 operands. Each operand address in the instruction might require its own mode indicator, or the use of a mode indicator could be limited to just one of them. Register versus memory. So a machine must have registers, of course, and with a single user visible register, usually called an accumulator, one operand address is implicit, and basically it goes to the accumulator and doesn't require any instruction bits. However, single register programming, as we saw in the previous chapter, is pretty awkward and requires a lot of instructions to get the same task done. Even with multiple registers, only a few bits are needed to specify the register. The more registers that can be used for operand references, the fewer bits that are needed. Number of register sets. Most contemporary machines have general purpose registers with typically 32 or more in the set, and these can be used to store data and can be used to store addresses for displacement addressing. Some architectures, such as the X86, have a collection of 2 or more specialized sets for data and displacement. One advantage of this approach is that for a fixed number of registers, yet functional split requires fewer bits. Sorry, that's an advantage. Requires a fewer number of bits to be used for the instruction. Address range. For addresses that reference memory, the range of addresses that can be referenced is related to the number of address bits. And granularity. For addresses that reference memory rather than registers, another factor is the granularity of addressing. In a system with 16 or 32-bit words, an address can reference a word or a byte at the designer's choice. So, in other words, the designer is faced with a large host of factors to consider and balance. We're not really sure about the effects of these. In fact, one study, this was Craig, 1979, compared various instruction format approaches, including the use of a stack, general purpose registers, an accumulator, and only memory to register approaches. Using a consistent set of assumptions, they found no significant differences in code space or execution time. So, in spite of all those trade-offs, they may not make a huge difference other than things are easier to program or more difficult to implement in hardware. Anyway, let's press ahead and look at 2 historical machine designs and how they balance these factors. First of these is the PDP-8, and you may recall this one as the first successful mini computer from Chapter 1. It had a very simple instruction design and used 12-bit instructions that operated on 12-bit words. So again, that the multiple there is 1. There's a single general purpose register, the accumulator, and the instruction format is pretty darn efficient. It supports indirect addressing, displacement, and indexing. And if you want to see the instruction format, you can look at it on figure 13.5, page 472, which will show the instruction format for that. So now let's look at the PDP-10. Okay, so as the old Star Wars saying goes, that's no moon, it's a space station. That's no mini, it's a mainframe. And the PDP-10 was a time-sharing system with easy programming emphasized because a lot of people were using it for more general purposes than the earlier machines. So it had 3 principles. One was orthogonality. Basically, other elements of an instruction are independent of the opcode. PDP-10 designers use the term to describe the fact that an address is always computed in the same way, independent of the opcode. So it didn't matter which opcode you were using, you were always computing the address in the same way. Each arithmetic type had a complete and identical set of operations, so you didn't have to worry about remembering that you could do certain things on floats versus doing things on integers. And direct addressing, base plus displacement addressing, was avoided in favor of direct addressing, so went with the simplest one possible. That did make an additional cost that was involved in making this particular monstrosity that you see pictured here, but it did make things easier on the programmer, and in some ways it was simpler to understand how it was working. So another choice that you have before you is you can choose to have variable length instructions, and basically it allows you to have a large repertoire of opcodes with different opcode lengths. The addressing can be more flexible with a lot of different combinations of register and memory addresses plus different addressing modes. It can also be done efficiently and compactly because you're varying the length of the instructions. This does, on the other hand, increase the complexity of the processor, and because of different lengths, you sometimes end up fetching multiple instructions if one is an example of another. So the principal price to pay is the increasing complexity of the processor, as we mentioned in bullet point 3, although the fact that we have cheaper hardware nowadays and use of microprogramming, which we'll get to in the next section, and the general increase in the understanding of processor design have made this a pretty small price to pay. However, RISC and superscalar machines exploit the use of fixed length instructions to provide improved performance. So variable length instructions are not the complete panacea to things. So one machine that made use of this was the PDP-11, and this is a picture of it from Wikipedia. It was designed to provide a powerful and flexible instruction set with the constraints of a 16-bit mini computer. So we're back to the mini computer as opposed to the PDP-10, which was the mainframe that we saw a couple slides back. And they had 13 different formats, and they had 0, 1, and 2 address instruction types. The instruction set and addressing capability were complex. There was some increased hardware cost, and it was more difficult to program than the PDP-10. The advantage is that more efficient or compact programs could be developed for this one. Another machine was the VAX, and the VAX wanted to look at how do you address the drawbacks to a relatively small number of fixed instruction formats. Addressing mode and opcode are not orthogonal, and only a limited number of operands can be accommodated, typically up to 2 to 3. To avoid these problems, they use 2 criteria in designing the VAX instruction format. All instructions should have the natural number of operands, the ones that make sense. So if you're adding, should be able to have 2 operands. All operands should have the same generality and specification. And the result is a highly variable instruction format. Instruction consists of 1 or 2 byte opcode, followed by 0 to 6 operand specifiers, depending on the opcode. And here's an example of one with 6 different operands. And the author of the textbook openly wondered aloud, well, why would you have 6 operands? And what this one does is it adds 2 packed decimal numbers, op1 and op2, specify the length and starting address of 1 decimal string. Op3 and op4 specify the second string. And then these 2 strings are added, and the result is stored in a decimal string whose length and starting location are specified by op5 and op6. And this thing had 12 different addressing modes, so again, quite complicated. So let's look at the X86 and ARM instruction formats, and this corresponds to chapter 13.4 of the text. As you might guess, the X86 instruction formats has a lot of different options that are available to you. There's always an opcode present, that's a good thing, but everything else is fairly fluid. Instructions are made up of 0 to 4 optional instruction prefixes, 1 or 2 byte opcode, optional address specifier, an optional displacement, and an optional immediate field. So let's take a look at some of these prefix bytes. Instruction prefixes. The instruction prefix consists of the LOC prefix and 1 or more repeat prefixes. And the LOC stands for lock, and that's used to ensure exclusive use of shared memory in multiprocessor environments. The repeat prefix specifies repeated operations on a string, which enables the X86 to process strings much faster than with a regular software loop. Segment override. This explicitly specifies which segment register an instruction should use, overriding the default segment register selection generated by the x86 for that instruction. Operand size has the default operand size as 16 or 32 bits, and the operand prefix switches between 32-bit and 16-bit operands. The address size, the processor can address memory using either 16 or 32-bit addresses. One of these sizes is designated as default, and the address size prefix switches between 32 and 16-bit address generation. With that in mind, we can now take a look at the x86 instruction fields. So there's the opcode. That field is 1, 2, or 3 bytes in length. Mod RM. Okay, this one actually specifies whether an operand is either in register or in memory. SIB, certain encoding of the mod RM byte specifies the inclusion of the SIB byte to fully specify the addressing mode. Displacement, when the addressing mode specifier indicates that displacement is used, an 8, 16, or 32-bit signed integer displacement field is added, and immediate provides the value of an 8, 16, or 32-bit operand. So you can use either immediate or displacement there. For ARM, all instructions in the ARM architecture are 32 bits long, and they follow a regular format. The first 4 bits are used as the condition code, and virtually all the ARM instructions can be conditionally executed as we've seen in the past. The next 3 bits specify the general type of instruction. The next 5 bits constitute an opcode and or modifier bits. Now, branch instructions are slightly different, but in general we can just say those 5 bits indicate the opcode and the modifier bits. And the remaining 20 bits are used for operand addressing. The regular structure of these instruction formats eases the job of the instruction decode unit. And again, that makes sense because a lot of times with ARM you have embedded hardware. So the ARM also has the thumb instruction set, and this is a re-encoded subset of the ARM instruction set. It's designed to increase the performance of ARM implementations that use 16-bit or narrower memory data bus, and to allow better code density than provided by the ARM instruction set. The thumb instruction set contains a subset of the ARM 32-bit instruction set encoded into 16-bit instructions, and it achieves savings in 3 ways. 1, thumb instructions are unconditional, so the condition code field is not used. Thumb has only a subset of the operations in the full instruction set and uses only a 2-bit opcode field plus a 2-bit type field. So again, you save 2 bits there. And the remaining savings of 9 bits comes from reductions in the operand specifications. For example, thumb instructions only reference registers R0 through R7. So you only need 3 bits for register references rather than 4 bits. The Thumb 2 instruction set, this is the only instruction set available on the Cortex-M microcontroller products. And it's a major enhancement of the Thumb instruction set architecture. You have the 32-bit instructions that can be intermixed freely with the older 16-bit Thumb instructions. And most 32-bit Thumb instructions are unconditional, whereas almost all ARM instructions can be conditional. It introduces a new if-then IT instruction that delivers much of the functionality of the condition field in the ARM instructions, and delivers the overall code density comparable with Thumb, together with the performance levels associated with the ARM ISA. Before Thumb 2, developers had to choose between Thumb for size and ARM for performance. So it kind of gives you the best of both worlds there. So let's take a look at assembly language, and this corresponds to section 13.5 of the textbook. Obviously, there's a heck of a lot more to assembly language than 3 pages, since we devote nearly a full course, CS266, to this. If you want to brush up on your assembly skills, there's a 20-page Appendix B in the textbook. I also recommend Knuth's The Art of Computer Programming Volume 1, which covers a assembly language known as MixAll, or Mix Assembly Language. This is the assembly language I had to learn while I was at Western, and it's great for understanding the algorithms used in that series of books, and can definitely help if you're interested in developing your algorithmic thinking. Finally, I recommend Human Resource Machine as a fun way to tackle the subject of assembly language programming. According to your pal Wikipedia, human resource machine uses the concepts of a corporate office worker assigned to perform tasks that involve moving objects between inbox and outbox and to and from storage areas as a metaphor for assembly language concepts. The player works through several puzzles in constructing a program to complete a specific task. It's interesting to note there's also a parallel programming one entitled 7 Billion Humans. So let's start at the beginning. Machine language. Processor can understand and execute machine instructions, that is, binary numbers stored in the computer. If you wanted to program directly in machine language, it would be necessary to enter the entire program as binary data. That's going to be both time-consuming and probably a bit error-prone. So let's take a look at an example. Let's consider a simple basic statement: n is equal to I plus j plus k. Suppose we wanted to program this statement in machine language and to initialize I, j, and k to 2, 3, and 4 respectively. We start the program at location 101 in hex and reserve memory for the variables beginning in location 201 in hex. We have 4 instructions. Load the contents of location 201 into the accumulator, add the contents of location 202 to the accumulator, add the contents of location 203 to the accumulator, and then store the contents of the accumulator in location 204. After translating all that into binary, this is what we get. That's pretty ugly for a pretty simple program, or for just a set of instructions that accomplishes one task. We might be better off doing that on a piece of paper or with a calculator. So what improvements can we make? Well, one is we can write the program in hexadecimal rather than in binary notation. And we could write it, the program as a series of lines with the address of the memory location and the hexadecimal code of the binary value stored in that location. Then we need a program that will accept this input, translate each line into a binary number, and store it in the specified location. It's still not very understandable from a human readability standpoint, but it is a bit better than just pure binary. Second improvement that we can make is a symbolic program. And basically here we make use of the symbolic name or mnemonic of each instruction. Each line of the input still represents one memory location, and each line consists of 3 fields. The first field contains the address for an instruction. The second field contains the 3-letter symbol of the opcode, and if it is a memory referencing instruction, then the third field contains the address. So, for example, address 101 has load into the accumulator 201. So that's loading the data value from location 201 into the accumulator. And to store arbitrary data in location, we invent a pseudo instruction with the symbol DAT, which indicates make data that corresponds to this decimal value. And for this type of input, we need a slightly more complicated program. The program accepts each line of input, generates a binary number based on the second and third fields, and stores in locations specified in the first field. The use of a symbolic program makes life easier, but it's still pretty awkward. In particular, we have to give an absolute address for each word. That means the program and data can be loaded into only one place in memory, and we need to know that place ahead of time. So, for example, if we were to add an additional instruction in here, we might have to move things forward. If we were to add something between address 102 and 103, then we would have to modify the addresses that are referenced in 103 and 104. So that can make things pretty ugly if we're ever going to make changes to it. So these absolute addresses are problematic. So let's look at a final improvement, and that improvement is assembly language. So assembly language uses symbolic addresses in addition to the symbolic opcodes. Each line still has 3 fields. The first is used for address, but a symbol, for example, formula, is used instead of the actual address. Second field is the instruction, and the third, for memory reference instruction, the third field also contains a symbolic address. So, for example, in the first line, we have labeled it formula. We're loading the value of I into the accumulator, and then we'll go and find I. And so with this last refinement of symbolic addresses, we have an assembly language. Programs written in assembly languages are translated into machine language using a tool called an assembler. In regard to the first field, there are some lines that have no addresses, implying that the address of that line is one more than the address of the previous line. So, for example, in the second one, adding J, that would be an example with no particular label. The assembler program must not only do the symbolic translation discussed earlier, but needs to assign some form of memory addresses to the symbolic addresses. The development of assembly language was a pretty major milestone in the evolution of computer technology. This is your second generation language. It was the first step to high level or third generation languages that are in use today. Although very few people still use assembly language in their professional lives, virtually all machines still provide one. And if they're used for systems programming such as compilers and I/O routines, and they can also be used to optimize things. Anyway, that's the end of the lecture, and so thank you for listening, and we'll see you